we have now H being equal to B e to the power minus rho g r to the power 4 T by 8 eta L r square. We know that at time 0, at initial time, the net height was capital H. So H was equal to capital H when time was equal to 0. So this quantity is 1. Hence we find that B is equal to capital H. Therefore, height as a function of time is going to be H e to the power some constant, say k, into time. This constant k is nothing but rho g r to the power 4 by 8 eta L r square. This is our required solution. Note that we might also have problems where we need to find volume flow rates for different situations. Let us consider one more problem of that sort. Let us say we have that plate-like problem again, through which there is a big plate, or there is a big container whose bottom is this, and we have a small rod or plate moving with velocity v0. In this kind of a problem, we found that v at any point through this height is nothing but v0 by capital H. Capital H is nothing but this height into y. This is our velocity profile. Now the problem is find the volume flow rate. To do this, we proceed in the exactly similar way. We consider that the length of the plate or the width of the plate in that direction is B. So this width is B. What we need to do is look at this container from this side to get an idea of how the area of cross section going to look like. Area of cross section for a small element of say length dy looks like this. This length is nothing but B. So through this area element, we will be having some fluid flowing through. Now what we do, we write q dot as what we wrote earlier. We integrate this entire thing from 0 to capital H, and we have something like v dA. So this is going to be 0 to capital H. V is nothing but v0 by h into y. Our dA, or the small area we considered here, is nothing but b dy. Now we integrate this. We take the constants outside. We have v0, b and h times y square by 2. Solve that further and you get this. This h now cancels off. This is equal to v0 b h by 2. Note that b times h is nothing but the entire cross-sectional area of the container we are considering. Let's say this is the container and this is our long plate, big container. This is what our bottom is. So the entire height is h and this width is b. So the entire cross-section is nothing but b into h. v0 by 2 is again our average velocity. So anything of this sort will give us the average velocity. Let us also consider the kinetic energy associated with the fluid in this case. Kinetic energy again is going to be of the form integral 0 to h half m, which is rho, let's say this is of rho and eta, rho, volume that is being considered, say the length of the plate is L or the length of the container is L, something like this. We are having this sort of a situation. This length is nothing but L, this height is h, and this width is b. So the volume considered for a small element, considered that a small area is nothing but b dy, we have the volume as b dy times L. Rho times b dy L is going to give us the mass. Mass times the velocity square is going to give us the kinetic energy. So this is nothing but, if you take the constants outside and replace v with v naught by h times y, we have half to rho b L into this constant, which is v naught square by h square. This integrated from 0 to h y square dy. This is what we have. This further solved gives us 1 by 6 rho b L into v naught square by h square into h cube by 3. Sorry, this is 1 by 2. Again we see that if we take this h here, we have the entire volume, so we have the entire mass. We have half into entire mass into v naught by root 3 square. This again becomes the root mean square velocity. So this is the kinetic energy associated with this kind of a flow.